All right, welcome back, mathematicians. We are on the second to last lecture of the semester. We are so close. We're going to be doing chapter 6, and we're only going to do sections 6.1 and 6.2. So today is just 6.1, and then tomorrow is 6.2. So section 6.1 is on volumes using cross sections. This lecture is kind of a bigger deal than the next one. This is get your base on how to find volume using integrals. It's going to use a lot of the stuff that we used last section, and section 5.6, finding the area between curves. Okay, so if you can see right here, I kind of drew a very poor picture. My pictures aren't too great in this section, so please bear with me. But we have just some solid outlined in black, and then wherever this blue plane is, that is where I take my cross section. So the cross section of a solid is the intersection of that solid and a plane. So if you ever seen those like butcher block knives, like in bakeries and stuff, they're really cool. Just like a big knife, and I cut into a solid, and that flat edge that I would reveal, that would be a cross section. So like if I have a wheel and I cut into it, depending on if I cut it down the wheel, I'll get a rectangle, and if I cut it through the wheel horizontally, I'll get a circle. So, but usually we do cross sections parallel to the y-axis. Nope, the x-axis. Nope, the y-axis, that one. And so that our plane is usually just some value of x. All right? So another way that we can calculate volume is by finding the base area. So from that cross section, I can find this area of this heart-shaped thing, and I can call that A. Well, that area, if I then make some height out of it, kind of like if you think about like a slinky, if a cross section's like a circle and then I pull it up, I now have a cylinder. So kind of like that. So I have that base area times its height. Well, I know area is usually something squared and volume is something cubed. So I multiply my base area times my new height that I just created by pulling that cross section up, and I get volume. So that's kind of the idea that we're going to. This section has kind of different ways that we think about slicing a cross section. All right, so the first method is kind of just what I said. We have a cross section, we multiply by its height, and that's called slicing by parallel planes, excuse me. So the volume, we're going to define that to be the volume of a solid of integrable cross-sectional area. So that means I can take the integral of that area from when x equals a to x equals b is, say that the volume is the integral from a to b of that cross-section area, which is usually and should be a sum function of x. Let it be square root of x, x squared, sine x, something like that. All right? Usually you're indicated to what that is in your problem. So how do we calculate the volume of solid? First, kind of always a really good thing to do is we're going to sketch the solid. I like to usually do two pictures, a cross section and a solid. So we're going to sketch the solid and a typical cross section. Is it a square? Is it a circle? Is it an oval? Is it just some random curve? What's that going to look like? So second, we're going to find a formula for a of x. once I have what that typical cross-section looks like, that should really help me find an equation for the area. All right. And then third, we're going to find our limits of integration, if we're not told them, of course. Remember last section when we were talking about limits of integration. I can't type and write and talk at the same time. We talked about how area between two curves sometimes are not given. The points of integration, I need to find them by setting those two equations equal to each other. All right, and then we're going to put all those three things together, and we're going to integrate AX to find the volume. All right, so here's an example. A pyramid 3 meters high has a square base. So if you see kind of where I've drawn right here, I drew it on its side with the axis supposed to be going through the center. That didn't really work, but I tried. So the cross section, wait, where am I? A pyramid 3 meters high has a square base that is 3 meters on its side. So 3 meters high up to 3 meters wide. The cross section of the pyramid perpendicular to the altitude x meters down from the vertex is a square x meters on a side. That's just fancy words of the cross section is a square and it's x by x. All right. Find the volume of the pyramid. So I drew my picture already. It's really fancy. And then I drew my cross section. I also sometimes like to draw my cross section within my 3D picture. But that's just me. You do you. Just a suggestion. So number 2 was to find the formula for AX, which is the area of a typical cross section. Well, typical cross section is a square. The area of a square is length times width. It so happens to be that our length and width are both x, so I have x times x, which is x squared. All right. And then I'm told that the pyramid has a square base that is 3 meters on the side. So that means that the max cross section is going to be 3. It's a pyramid, so the cross section has to come to a point. So that means we're going to go from 0 to 3. So I really don't know how else to best explain that x equals 0 is where we're going to start because pyramid. And then x equals 3. Base of triangle. No, base of pyramid. Is square. Okay, cool. And now we're going to integrate to find the volume. So we saw that volume is going to equal from A to B, in this case from 0 to 3 of our area, which is A of x, dx. Now I hope by now you guys can integrate x squared because you guys are super smart. So we're going to add 1 to the power, so we'll get x3 and then divide by that same number. And then I'm going to evaluate it from 0 to 3, which means I'm going to have 3 cubed over 3 minus 0. And that's going to simplify to 9. And I scroll up and I was given some units and they're all in meters. So volume is something cubed, so meters cubed. And that's our answer. So not too bad, but there's still a lot more that we need to go. Slicing by parallel planes isn't too common of a one. The next two are probably the more common ways to find the area of a volume. Sorry, the area of a volume. The volume using the integral of the area. All right, so solids of revolution, the disk method, which I forgot that word. Okay, cool. So definition, a solid generated by rotating a plane region, so a cross section, but a cross section if I sliced it down the y-axis. So I took my knife and on the y-axis and I cut right down, and I got this beautiful cross section. So this plane region, and I'm gonna rotate it about an axis. Doesn't have to be the x-axis. We'll also get to what happens when I rotate around the y-axis. It's pretty similar. That's called a solid of revolution. So I'm gonna take this cute little curve, I'm gonna spin it around 360, and I'm gonna get this really cool shape. This kind of looks like a bullet, which, read the Rube McKinsey. Okay, so, I don't know. Oh yeah. So now my area cross section, well, I'm gonna take my curve and spin it around. So that means that my area cross section now is going to be pi times whatever the radius is. Well, I'm taking it from that axis. Radius squared. So let's call that big R of x. And I'm going to square it. And this comes from the area of a circle. So now my cross sections are going to be circles because I'm rotating this little curve around. That makes a circle. I don't know how else to explain that. I hope that makes sense. So that's why we get pi r squared, where r is some function, right? So the volume of the disk, so this is called volume by disks. We're going to get to one that's called volume by washers. 6.2, there's something called shells. I'm trying to make sure that there's no other fun words. That's called vertical lines, and that's shells. Okay, yeah, cool. So, disk, washer, shelves. The volume of the disks by volume by disks for rotation about the x-axis. We'll call that V, and that's going to be always, right, A to B of the cross section, but we can get a little bit more specific because that cross section is a circle, and I can go from A to B of pi r squared, where r of x is our radius, r, and usually the curve that I am flipping around, all right? So let's do a fun little example. So the region between the curve y equals x squared, which is this one up here actually, or not squared, square root of x, from 0 to 4, and the x-axis is revolved about the axis to generate a solid, and we're asked to find the volume. So that's actually what's happening up here. So this little red line, that's kind of my radius. So that radius is going to change in over time, and by time I mean my variable x. So, and when I rotate it, I'll get something like this. So we go down here. So I already drew my figure. I know my bounds, I'm told them from 0 to 4. And from the picture, I can see that my radius is going to be the square root of x. So if I put that all together, I'll get that my volume is equal to 0 to 4 pi square root of x squared dx. All right, and then I'm going to pull this pi out because he's just a constant. He's just a number. and I get square root of x squared, that's just x, dx. Technically it's the absolute value of x, but we're not getting into that because all of our x values are already positive. And then let's go down. So we get pi x squared over 2 from 4 to 0. So whenever I have a constant out front, I kind of like to do the fundamental theorem and not include that constant. It's easier to do all this multiplication and whatever right here and then just multiply once I simplify and subtract some things, okay? Instead of multiplying everything by pi. So what do I get? 4 squared, which is 16 over 2 minus 0. Ooh, let's make those parentheses match. And that simplifies to 8 pi. And I don't think I was given any units in that problem, so I don't owe anybody any units back, so we're good. Okay, cool. So now I'm going to show you a problem, and it's going to look really similar to a problem that we're going to do later, which is why I want to show it to you, because I don't want you to get confused. This is still disks, okay? So I want to find the volume of the solid generated by revolving the region bounded between still square root of x and now this line y equals 1. Well, earlier I did the x-axis. Well, now I kind of move that up, and now I'm having this one line and x equals 4, but now I'm rotating around this line. So I rotate around the axis and I get this big one, and now I have a smaller one, but I'm still using the same curve, y equals the square root of x, but I'm revolving around a smaller radius. So my r of x is going to be a little different now. All right, so r of x is going to equal wherever I start revolving from to where I stop. So that little red bar right here, that's always going to be from this point to here, x equals 4. That's going to be a radius. So that's going to be my top minus my bottom. So that's the square root of x minus 1. Okay? So, and now I need to find my integration points. So I need to find where y equals 1 intersects y equals the square root of x. Or I want to call these limits of integration. All right, and that's obvious when x equals 1. All right, and we actually already know the other limit of integration because we're told that we're finding the area of the region bounded by x equals 4. So we have x equals 1, found it, and then also x equals 4, and we're given this one. All right, so I now have my volume from 1 to 4, pi square root of x minus 1 squared. And now I don't want you to tell me that this is x minus 1. That is not how foiling works. I know all of you passed algebra and know how to FOIL. Okay, to pull that pi out from 1 to 4, this is going to be x minus 2 root x plus 1 dx. And that's going to equal, leave that pi out for a little bit, x squared over 2 minus So that's going to be 2x to the 3/2 times 2/3 plus x. We're going to integrate that from 4 to 1. And to save ourselves some space and time, we work that out. And we will get 7 pi over 6. Alrighty. So, quick tip when you're doing, since this is x to the 3/2, 4 to the 3/2, I would take the square root, so that 1/2, and then cube it. Just a quick tip. So you'll get like 8, right? So the tricky part about this problem was seeing that our radius was top function minus bottom function. This is kind of where stuff from 5.6 comes into play. So if you're kind of struggling with that, this is going to be, it's going to be really helpful in this section. And I think a lot of the problems might come with pictures, but if not, definitely try to draw your pictures, especially on your homework. Okay? So now we're going to talk about the volume by disks for rotation about the y-axis. So we talked about the x-axis. We even talked about rotating about other things parallel to the x-axis. So now let's talk about integration about the, rotation about the y-axis. We talked about integrating area between curves about the y-axis, and it wasn't too different. So now we're going to integrate from C to D, which is just kind of the equivalent to A to B on the y-axis. And our cross-section is not going to be A of x, it's going to be A of y. So when we rotate about the y-axis, all of our functions are going to be in respect to y. If we're rotating around the x-axis or something parallel to the x-axis, everything's going to be in x values, okay? So let's do an example. So we're asked to find the volume of the solid generated by revolving the region between the y-axis and the curve x equals 2 over y. Definitely tells you, it's a good hint if you're already given your curve in an x equals form, so you already kind of have a of y, if not part of a of y. And we're going to go from y between 1 and 4, and we're going to revolve about the y-axis. All right, so I kind of drew very poorly the curve, and then what it will look like if I rotate it. So kind of like a cool little volcano. All right, so my limits of integration are y values, not x values, and I'm also actually already given them 1 and 4. So that's pretty neat. Our radius is, since we're revolving just about the y-axis and there's only one curve, that curve is going to be my radius. So that means that r of y equals 2 over y. It sounded like I was saying au revoir. Do you know what that means? Okay. So my volume equation says that I'm going to go from 1 to 4. I'm already given those up top. And I'm going to put my area, which is pi 2 over y squared dy. All right? And then I'm going to simplify that first just to help me. So 2 squared is 4. And then I'm actually going to write this as y to the -2 dy. That just helps me integrate. So I'm going to pull out 4 pi. He's just kind of in the way. So then y, I'm going to add 1. Oh wait, I don't need my integral anymore. Going to add 1 to y, so it's -1, and I'm going to divide by -1, we're going to evaluate that from 1 to 4. So I'm actually going to do a little sneaky trick and move this negative out front. So I get negative 4 pi 1 over y from 1 to 4, which will give me negative 4 pi 1/4 minus 1, which is negative 3/4, negative 4 pi, negative 3/4. Negatives cancel out, 4s cancel out, and we should just get 3 pi. Yay! So not too bad. Definitely the challenging part is finding your radius. I hope integrating and plugging in is not the hardest part for you all. But just know if I'm given one curve, so x equals 2 over y, and I'm given like this inequality right here, whoops, no, and I'm told I'm going about the y-axis, is a really good indicator that I'm only going to be dealing with this guy when I'm trying to find my radius for my disk, and these guys are going to be my bounds. All right. So solids of revolution, the washer method. So this is different than what we just did. So I still have two curves here, big R and little r, but now I'm rotating both of these curves, which gives me a washer. So basically a really fancy vase that doesn't have a bottom. So some messed up toilet paper. Right, so we call big R of x the outer radius, and we call little r of x the inner radius. All right, so this here will give me something that's hollow. Up here, not this one, I didn't get anything hollow. I got a solid bullet-shaped thing. All right, because I was rotating about a different line that wasn't the axis. Here, I'm still revolving around the axis, but now I'm doing the curve that's the area between two curves. So take what I did from 5.6 and put it on steroids. But we're gonna master it, so it's gonna be super easy. All right, so this is called the volume by washer. Washer is the little thing that you put on around the bolt so it doesn't mess up the furniture if you ever built IKEA furniture or something. They kind of look like this. Nope. That's a washer because it's hollow on the inside. Okay? Terrible drawing. So the equation for this one is going to be obviously the area of the cross section. We're used to this generic excuse. And now we're still going to go from A to B. I'm still revolving it around the x-axis, so pi is going to be involved, but it's going to be big R of x squared minus little r of x squared dx. So this is important. I could even go further enough using sum and difference. I keep writing my r's like they're the real numbers. If you think about it, it's kind of like we did when we were doing area between two curves. I took my higher one, in this case we're using that outer radius term, and I'm subtracting the area that's below the lower one to get the area in between. Well, now when I rotate it, I don't want this area inside, which would be the area if I rotated just the inner radius. So I take my outer radius and I revolve it around the axis, and I get that volume. And then I subtract this inside hollow part, which I get from revolving r around, which is why each r is squared, and I'm not combining them and then square them like I did up here. All right, so washer, I'm gonna have two things squared. Disk, and I'm revolving around something that's not the x-axis, I'm going to have to make it look like curve minus line rotating about. I know I'm switching between a lot of things right now. I just really don't want you guys to get confused. All right, so that's the main difference here. Curve minus line I'm rotating about. These are two lines that I'm rotating about, and I want to find the volume between them. All right. I suggest using this equation rather than this bottom equation just because it saves you a lot of time. There's no reason to use the bottom equation. Just kind of showing you where it comes from. All right. So now we're going to put this into practice. So the region bounded between the curve y equal to x squared plus 1 and the line y equal to minus x plus 3 is revolved around the x-axis to generate a solid. Find the volume. All right, so I've already drawn my picture, a plus. I know how to draw x squared plus 1 and minus x plus 3. I better know how to draw a line, and a simple shift of x squared shouldn't be too difficult. But if I didn't know, I can do kind of what I would just to find the area between them. So I would, let's call this one y1 is going to be x squared plus 1. And minus x plus 3 is going to be y2. So y2, y1. All right, and I'm going to set them equal to each other because I'm trying to find what these 2 points are. Obviously, looking at the graph, I know what they are, but let's just say I don't have that. So I'll get x squared plus x minus 2. 1 minus 3, yeah. Nope. 2 equals 0. So that's going to give me x plus 2, x minus 1 equals 0, because x plus 2, x minus 1 multiplies to negative 2 and then adds to 1. So that means that x equals negative 2 and x equals 1. So those are my points of integration, our limits of integration. So this is at 1, oh my goodness, 2, and this is at negative 2, 5. Okay. Just plug those really quick into there. And I knew what they were. All right, so we're still revolving around the x-axis, so I don't need to like do anything like minus the curve, minus the line I'm rotating about. I'm just staying with the volume, staying with the x-axis. So that's good. So now I need to find who is, whoa, big R and who's little r. Well, just like we did at 5, 6, we're going to plug in a number between negative 2 and 1 to figure that out. So what's always a fun number to plug in? 0. So y1, I'll get 0 squared plus 1, which is just 1. y2 equals negative 0 plus 3 equals 3. So ding, ding, ding. y2 is big R of x, and y1 is little r of x. All right, so now I can make my volume equation. Volume. So I'm going from negative 2 to 1 of pi, and then big parentheses, big R of x is y2, so negative x plus 3 squared minus little rx, which is x squared plus 1. So minus x squared plus 1 squared dx. So let's make that a little clearer. So this is little r x squared, big R x squared. Okay, cool. Alrighty, so going from -2 to 1 pi. So let's FOIL. So negative x squared plus 3. It's going to give me x squared minus 6x. Yeah, 2ab. Yeah. Plus 9 minus, keep your parentheses because that minus is going to distribute. Biggest mistake is just getting the integral right, even after getting these r's right. So then we're going to have x to the 4th plus 2x squared plus 1 dx. To pull that pi, I don't need them right now. See in a little bit. -2 to 1. And then let's see, x squared minus 6x plus 9 minus x to the 4th minus 2x squared minus 1 dx. So let's do minus x to the 4th. Ooh. Minus x squared minus 2x squared, minus 6x plus 8. Cool. All right, now we're going to integrate. Oops, I don't need my integral from integrating. So negative x to the 5th over 5 minus x 3 over 3 minus 6x squared over 2, we'll simplify that a little bit, plus 8x. I almost put a dx from -2 to 1. Okay. Boop, boop. See how annoying it would be to add a pi on those 4 things. I could just multiply by one thing in a little bit. Oh golly. So I'm going to plug in 1. So -1/5 minus 1/3 minus 3 plus 8 minus, oh god, 2 to the 5th. 2 squared is 25. Big number. I'm going to plug that into my calculator later. But it's -2 to the 5th, so careful. -5 minus -2 cubed over 3 minus 3 -2 squared plus 8 times -2. Running out of room. All right. Oh, I think that's supposed to be big. There we go. So then after all of that, we should get 117 pi over 5. All right. Let's do, I wasn't planning on doing one more, but we could also see a case where we were doing a region bounded between, or doing washers, and yeah, let's do another problem because I want you guys to see as many problems as you can. Woo! So we're gonna do one with y values because we can do the same thing for washer as we did with discs where we revolve around the y. So the region bounded by the parabola y equals x squared and line y equals 2x in the first quadrant. Call it just first quad. So it's revolved around the y-axis. To generate a solid. It's gonna look kind of like a cup. And we're gonna find its volume. Not in the cup. I keep writing volume. Ooh. Volume. Okay. So let's do a quick little sketch. This is real time. So yeah, that should be good. Let's do y equals x squared. So that's 1, 1, 2, 1, 2, 3, 4, 5, 5. Something kind of like that. And then 2x. And the first quadrant is going to kind of like that. Oh, I did that wrong. Okay, there's one curve. Let's make another one a fun color. Boom. Sometimes I'm writing notes in class and I try to hold my pen down after drawing a line and it doesn't make a straight line because I'm writing on paper. Okay, so this is our solid in here. Gonna look like a cute little cup. So we're revolving around the y-axis. So that means my radius is going to be, when I was doing area between two curves about the against the y-axis, I can't do top and bottom. It doesn't exist in the y-axis world. I'm going to think of it as outer versus inner. My farther away minus my inner radius. I think I called it this one. Because kind of outer and inner, I can interchange that if I'm talking about x and y. I called r of x and little r of x, but I really should be calling them r of y. So little r of y and big R of y, because we're rotating around the y-axis, so that means everything needs to be in terms of y, which isn't too bad. So that just means that y equals x squared is going to turn into x equal the square root of y. And we know it's positive y because I'm told I'm in the first quadrant. And I know that y equal to 2x is going to turn into x equal to 2y. Nope, not 2y. Y over 2. There we go. So then I have my picture. I have two possible big R, little r. But now I need to find my points of integration, and then I can find who is my outside versus inside. So I'm going to set y square root of y equal to y over 2. So that's going to be y equal to y squared over 4. So 4y equals y squared, which means either y equals 0 or 4y equals y. Yeah. So right? So I have this little point right here, and this little guy right here. And that's at 0, and this is at 4. Okay? So I have my limits of integration, and now I can find who is outside versus inside. So a fun number to plug in between y equals 0 and y equals 4 is y equals 1. So let's call x1 the square root of y. That's just going to be the square root of 1 equal to 1. And let's call x2 the other curve, y over 2. So that's going to be 1/2. And that's definitely smaller than 1. So we'll call x1, which is the square root of y, big R. And we'll call x2, which is y over 2, little r. And for the life of me, I won't remember to put y's. It's all just a dummy variable. Anyways, so plug and chug into our volume equation, because I know who big R and little r are, and I know my points of integration, and I know I'm going around y. So I know everything should be kind of right. So Avengers Assemble. God, what is that actually from? Okay. Whew. My cat scared me. 1 second. Are you okay? That's why we don't go in there. Okay. Alrighty. From 0 to 4, I haven't pulled my pi out, so we're going to take square root of y and square it, and then I'm subtracting y over 2, and I'm also going to square that. And so that I am mathematically correct. Big parentheses around it, times dy. All right. So simplify that, and I get y minus y squared over 4 dy, and now we can integrate. So I'll get that y squared over 2 minus y cubed over 4 times 3, because I'm also adding to divide by 3, from 0 to 4. So pi, let's plug in 4. 4 squared is 16 over 2 minus 4 cubed is 16 times 4. Oh god. 40 plus, what's 4 times 6? I had to stay late in elementary school because I didn't know my 7s and 8 multiplication tables, and I still don't know them. But 4 times 6 is 24. So, no, it's not. Yeah, 24, 64. Okay. 16 times 4 is 64. Divided by 12 minus 0. And that should give me my grand finale of 8/3. No, 8 pi over 3. All right. So I don't think I was given, no units, so I owe no units. And we're done. Okay, so I hope you guys got a lot of different types of examples for washer and disc and slices. Remember, the homework on this section is optional, but it is extra credit. So I highly suggest doing it. You can always get over 100 on your homework grade, which I honestly think is pretty great. All right, I will see you guys tomorrow for our last lecture.